Today's topic is the moving average model. As we discussed, the moving average is MA model. It is the linear summation of the white noise, but in front of the white noise, for at each time, we plug some constant. Yep, it is the as a Greek letter is named theta. Okay, so we are going to use the theta. It is the MA parameters, and absolutely the WT at any time is not only at t, but also t minus 1, t minus 2, t minus 3 is up to t minus q. That is the IID, white noise. I mean the normal distribution, mean equals 0, and the variance is the sigma square, as we knew. So now we are going to use the MA operator. It looks like this. So simply we just multiply the white noise, I mean the theta B white noise. It will be same as 1 plus theta 1b plus theta 2b square is up to theta q bq times the white noise. And now we can take the multiplication. So 1 and white noise will be WT, and theta 1b and WT will be theta 1b WT, and the next one is a theta 2b square WT, and the last one will be theta q bq WT. And now here's a B times WT. You know the B was the backshift operator, and the power is actually 1. So now I just take the WT first and theta 1, and it will be 1 time backshift. And here is the B square, that is the backshift twice. So the third term will be theta 2 WT minus 2. It's a 2 backshift. And the last one is a theta Q. And the power is a Q, that is the Q times backshift. So the white noise at time t minus Q. So please compare to this one and this one. They are exactly same. So simply we can rewrite the time series xt will be same as this. Using the MA operator, the theta B times the WT. You know, as before for ARP model, we used the AR operator, which was the phi B, but we multiplied to xt is equal to the WT, and the phi B was 1 minus phi 1b minus phi 2b square is up to p. Okay, it's a phi p pp, right? So please make sure the MA operator, that is it looks similar, please compare to the AR operator here, right? But it's up to Q in MA model, it's up to P in AR model, and it just take the summation, right? It just take the summation because on the right hand side, the MA model has the linear summation of the white noise, but it's also the AR model was, the XT was the linear summation of the axis itself. It's an auto regression model, but we multiply the phi b to xt on the left hand side, so there was the negative signs. Okay, so similar as the ARP model, we can define the MA model. It's MAQ model. It looks like this. It's using the MA operator, the phi b. So here's another example. An example here is MA1. So here's a MA1, and it's like this one. Before we discussed the MA1 model, we took the expectation. It was easy. Here's a white noise and white noise. So expectation of the white noise. I can give you as more details. It will be expectation of the white noise at time t plus theta 1 expectation of another white noise at time t minus 1. Then identically the expectation will be 0, and that will be 0. So the expectation of xt will be equal to 0, and we had the gamma h. Can you remember the notation of the gamma? It was the auto covariance. When h equals 0, that means it will be exactly same as the variance. So the variance at time t, when h equals 0 is itself, it was 1 plus theta square times the sigma square for MA1. H equal 1. H equal 1 means with the neighbors, with the t and t plus 1, or t and t minus 1. So the covariance is when h equal 1 with the neighbor. That was the theta sigma square. It is the MA1. So it's only the linear summation of the white noise at time t and another white noise in t minus 1. So when h equal 2, there is no covariance. It's not only h equal 2, but also 3, 4, 5. They are all 0. It's no correlation. It's no covariance. So simply we can say the h is bigger than equal to 2, that means it's 2, 3, 4, 5, and so on. Then the autocovariance will be 0. So now we can take the ACF. The ACF stands for the autocorrelation function, which was the using the notation of the rho h. It can be defined as the gamma h. The autocovariance divided by the gamma 0. Because gamma 0 was the variance. So we can take one by one. Let me make the spaces here. So rho 1, that means when h equal 1, so we just take this one in the numerator divided by the variance. 1 plus theta square is a sigma square. So simply cancel out the sigma square. So the theta over 1 plus theta square will be the A shift when h equal 1. Let me take another one. Is rho 2 is A shift at h equal 2. So we have to take this one, nothing, over the variance. Whatever in the denominator, that will be 0. When h is not only 2, but also is bigger than or equal to 2. So simply I can define the A shift, the rho at any h, it will be theta 1 over 1 plus theta square when h equal 1, and the others, h is bigger than or equal to 2, it's nothing. Yeah, so it is the A shift for the MA1 process, MA1 model. So please remind what was the A shift for MA1, and it is another example. It will be the last example today for MA. Before, for the AR model, we discussed the causal. It's a causal conditions, it's assumptions for the AR model. That was for AR1, we need the condition, the absolute value of the phi must be less than 1. Then we can take the infinite summation of the white noise. Infinite sum of the white noise is from 0. Or we use the capital phi and the white noise, right? Yep. General. It's a general case. For example, it's ALP. So I gave you a homework. It's a p equal 2 to get the capital phi, and also we use the operator as big phi operator. It's a WT here. So in the AR model, we had a causal. We are going to discuss is another condition for the causal when p equal 2 is later. But now we have a MA model, and we need another condition is invertibility. So that is look at this one. It is a model number 1 with the white noise is a mean equal 0, and the variance is a 25. And here is another model number 2 with another white noise, but still the same mean equal 0, and the variance equal to 1. But here's the coefficient is 1 over 5. In model number 2, there is a 5. So now let me try to get A shift. Okay, let me try to get the A shift in model number 1 and model number 2. So let me try here. For model number 1, how much is the theta? You know, both of them is model number 1 and model number 2. They are all MA1 model. So in model number 1, the theta, that is 1 over 5. So I can take the A shift when h equal 1, that will be 1 over 5 plus 1 over 5 square. The other one, model number 2, it is another MA1, but theta was just 5. So in the model number 2, the A shift when h equal 1, we don't have to take h equal 2, 3, 4, 5 because it's always for the MA1 model, it's always the other A shift is h is bigger than equal to 2, is always nothing. So we just take only the case h equal 1 here and h equal 1 there for A shift. So using this one, because always that is the A shift when h equal 1 for MA1. So simply we plug the theta here, 5, 1 plus 5 square. So we had two different MA1 model, but now please look at this. Let me see. It will be 1 over 5, 1 plus 1 over 25. Then it will be 1 over 5 over 26 over 25. Then I can make with a common denominator. So it will be 5 over 25. Then now I can cancel out. So the A shift when h equal 1 for the model number 1 will be 5 over 26. Let me try again for model number 2. So here's a 5, 1 plus 25 will be 5 over 26. What I want to say now, the A shift at h equal 1 from model number 1 and model number 2, they are same. Interesting. So let me go back to, oh my god. So let me go back to here. You know, at the beginning, we had two AR model. I'm sorry, MA model, MA1. Here's 1 over 5, and there's a 5. But from both, we got the same ACF. That means it's invertible. They are invertible. See, there's a 5. And here's a 1 over 5. So with a different theta, we can take the same A shift. So it is another condition. It is another C. Is look at this. It is the non-uniqueness, right? From the same A shift for MA model. It means it's invertible, right? So please remember the conditions. Is a causal for AR model and invertible for MA model.